Good. Thank you. That helps a little, Mark. All right. Well, good afternoon, everyone. Welcome to I think today's May 7th version of the HamSCIence Zoom call. We've got our last presentation of the year. We're going to make it, I think, a memorable one with Mary Lou West talking about cosmic rays in the heliosphere. See, we've got a pretty good audience that has come here to join us. So I think we'll turn it over to Mary Lou and let her get started.
Well, thank you, Gary. Let's see if we could do this.
Just remind everyone to mute yourselves, and then we'll let Mary Lou do the talking until we have time for questions. Good, there's your title slide.
Yeah, but we haven't got. I have to stop again. Sorry. Um, Got to try it the right way. Okay. Okay, I just started from the beginning. Unhappy otherwise. So I want to tell you today something about cosmic rays and what they can tell us about the heliosphere, which is, of course, of more importance to radio people than some of the other stuff. But I think cosmic rays are just really, really cool things. All right, so the outline of the talk, try to get you motivated to be interested in these little things. A little bit about the history of how we learned that they really were cosmic rays, and the GZK limit, which is one of the important physical things about cosmic rays, talking about the whole universe. And then the Auger Cosmic Ray Observatory, which measures those. It's in South America. And then locally, what this tells us about the solar system, the Earth's magnetosphere, and then the sun's heliosphere, and how they interact with these cosmic rays. And then I want to tell you about the Montclair State University experiments that I did with some students a few years ago. And that was really fun. We borrowed some equipment and we had a lot of fun using it. So why are cosmic rays interesting anyway? Uh, First of all, they are higher energy particles that can be made on Earth. So we have synchrotrons and all sorts of particle accelerators here on Earth that work very hard to accelerate these small things going in really large circles to very high energies. However, they're nowhere near the sort of energy that rains down from the sky. Orders of magnitude, many, many powers of 10 more energetic what comes from the sky than what we can make here. They offer really solid proof of Einstein's theory of special relativity, and in a fairly straightforward way. A college student can measure things and go, oh, Einstein was right. Yes. Um, they are still of mysterious origin. There are several possibilities of where they could come from, and we don't know which one it is. And it is really um, inherently difficult to figure out where they could possibly have, which one of these it could possibly be. They're interesting also because they're hazardous to human exploration of the moon and of Mars. We here sitting at the Earth's surface are protected by our magnetosphere of the Earth. And so the cosmic rays, many of them never get to the surface of the Earth. But I'm going to tell you, of course, about some that do, but very few do. But you can measure them then. But if you're out beyond the Earth's magnetosphere in some spacecraft and you're going to the moon, or in fact to Mars, you're going to be exposed to quite a lot of this highly ionizing radiation, and you should take precautions about it. And in particular, um, the amount of radiation that hits these unprotected areas is sufficient that we will have to live underground um, and not be out on the surface very much because you get a full body scan every 5 days, and that increases your risk of cancer. Then we're going to talk about the interaction of the cosmic rays from other stars and galaxies and whatnot, and how they impact the sun's heliosphere. Well, first I want to say something that is often confusing to people because they're called cosmic radiation, and radiation usually means to us light, but it was misnamed in historical times. So there you go. And so I'd like to make clear what's the difference between light and a particle, because these are particles. Light is energy with no mass. It's usually a sine wave of electric field and magnetic field arranged 90 degrees from each other. And in regular visible light, we say Roy G. Biv. I don't know. Do you say that in Canada as well, Normand? I don't know. Um, Normand, do you say Roy G. Biv like that?
Nope.
Nope.
I don't know what I'm not, that's the first time I see that.
Aha! Aha! So can we have somebody who's from the United States who knows what Roy G. Biv is? Can't hear anybody well.
Red, orange, yellow, green, blue, etc.
But the et cetera is important. After
Yep,
blue,
yep.
Violet.
indigo,
Indigo,
violet,
violet. Yep.
Okay.
right? Okay. And I think a little story about that. Sarah, do you know who named them these colors in particular, and that we should pay attention to these particular colors? Do you know who did that? His first name was Isaac
It must be Newton.
Newton.
Newton, right? So Newton used a prism, divided the beam of light from the sun into the colors, and of course it's a continuum of colors. And he said, we can't say continuum, we should say really colors. Oh, so it's red at one end and violet at the other end. What shall I call the ones in the middle? And uh, then he thought, we should have a certain number, and the certain number should be 7 because 7 is a magic number. Okay, so 7 has been a magic number for a long time. And so it had to be 7. So he got red, orange, yellow, green, blue, violet. Ooh, we need one. So he made up indigo and stuck it in there. Indigo is the color of ink that they used in pens in those days. And everybody then knew what it is. Nobody today knows what it is. It's the color of brand new blue jeans. Anyway, so that's Roy G. Biv, the colors in order of a rainbow. Okay. A particle, on the other hand, is energy which has mass as well. So we have in those things protons, neutrons, electrons, pions or pi mesons, muons or mu mesons, positrons, and neutrinos, and then a whole bunch of other little things as well. Many of these people have heard of, and they mainly go in a straight line. Not all the time, though. Okay. Here's a lovely diagram I found of the electromagnetic spectrum, which is the colors of light. And of course, visible light is a very small bit in the middle there and centered on green. So that's where our eyes are best to see the colors. And then on the right, we have ultraviolet, X-rays, and gamma rays. On the left, we have infrared, microwaves, and radio, which is a very low frequency light wave, but is very useful for lots of things, including communications. All right. Particles, when they run into other particles, tend to splatter into pieces. It's like cars on a highway. And if they run into each other, they fall apart into many pieces. So cosmic rays are particles. They interact with the Earth's atmosphere when they finally get here and produce what's called an air shower. The air shower means that the primary cosmic ray, whatever it was, is now broken into pieces. And then each of these pieces breaks into more pieces, and they break into more pieces. And often from a single particle hitting oxygen or nitrogen or whatever it manages to hit in the upper atmosphere, you may get 1,000 little pieces coming down through the air, smaller pieces. Some of them are light, some of them are other particles. So in particular, the incoming particle is almost always a proton, a single proton. It hits an oxygen or a nitrogen atom or molecule in the air and becomes pi mesons, uncharged, charged plus, and charged minus. So you have three of them. Then each of them breaks up into things. And by the time, and many of them just decay into light. And so there's nothing much left to get to the ground. The ones that get to the ground are the mu mesons. There are a few of them, but they are very sturdy little things, and they get to the ground. Here's another picture I thought was lovely of the air shower, and you can see different things disintegrating into other things, and the mu mesons which come down through past a mountain, past a valley, and get to ground level. One of the things that one can do if you have a sensor for these things is to take it up a mountain and measure things at various distances above the surface of the Earth. We did not do that part. There are very few mountains in New Jersey. I want to tell you some history about the development of our knowledge about cosmic rays. um, so the sensor that people liked early on is called an electroscope, and there's a picture of one in the right-hand side here. It's a glass jar with a cork in it, and then you have a metal rod that comes through the cork, and at the bottom of the metal rod, there's a little hanger, and you put down two little pieces of aluminum foil, or one piece of aluminum foil bent in the middle, and then at the top of the stick, you put a little metal ball of some sort. And then the idea is to charge up the metal stick, because when it's uncharged, the two pieces of aluminum foil just hang down neatly next to each other. So then you rub your hair, you rub a balloon, you rub the carpet, and you touch that to the top of the thing. And you do that several times, and the electric charge, the electrons run down the little stick and they come to the aluminum foil and they charge it up, and then things that are of like charge repel each other. So the two pieces of aluminum foil repel each other, and you put more on it, repels it more. You put more on it, repels it more. It's really cute and easy to do. And they found that if you waited a long time, it would gradually discharge itself, and the little aluminum foils would come together. But if you had a piece of uranium ore, uranium was known to be something special. You'd bring it up, and the things would whoop, go together fairly quickly. So the uranium ore was giving off something that discharged the electroscope. Didn't know what it was, but something was coming from the chunk of uranium ore. I found a picture of it there, what uranium ore looks like, a piece of dirt. Okay. And then people realized that the rate of discharge, how quickly the electroscope fell back to vertical, could be used as a measurement of the strength of the radiation given off by these materials. So you could get high quality uranium or lesser quality, or a bigger chunk of it or a smaller bit of it. And it would all be quite linear with the amount of time it took to discharge the electroscope. Have any of you ever played with an electroscope?
I
Things
remember
to do.
seeing that in science books as a kid.
Oh, but it's great fun to play with one. You can make one in the kitchen. Okay. It had been noticed that the electroscope would discharge at a very slow rate, even outside the presence of any radioactive material like uranium. So that would take, hours and hours and hours, and nobody knew what that was going on. So Victor F. Hess decided he was going to study the source of this background radiation. And he figured it was from ore in the ground around us, somewhere in the dirt. And his question was, how high would he have to go in a balloon to get above the Earth's background radiation? So he had an electroscope, got it charged up, was watching how it gradually discharged, and he went up in a balloon. So this was in 1912, before the war. Here he's the man in the middle there in the balloon basket, and he's got some equipment. And there's a picture of the balloon going up. What fun. And he discovered that the rate of discharge of his electroscope got smaller, smaller with the altitude until he was a kilometer above the surface of the Earth. But then the rate began to increase. He was very surprised. Twarn't supposed to do that, you know. And by the time he got to 5 kilometers altitude, the rate was even more than it was at the Earth's surface. So he's looking up thinking, where's the big piece of uranium in the sky that's causing this thing to discharge? He realized that this radiation did not come from any aura on Earth, and he called it cosmic radiation. And so he's the one that named that. Bad choice. And then he won the Nobel Prize for that. So some 20 years later, he got the Nobel Prize in 1936. He won half the Nobel Prize in physics for the discovery of cosmic rays. I think he was very happy. Carl Anderson won the other half of that same Nobel Prize for discovering the positron in cosmic rays, which he had done in 1932. So on the surface of the Earth. Carl didn't go up in any balloons. A positron is an electron which is positively charged. So it's the same mass, same size, same thing as electron, except instead of got a negative by it, it's got a plus by it. Can anybody, well, maybe I should just tell you, does anybody know how you could figure out that you were seeing a plus one instead of a minus one? David?
The bubble tracks.
Stick it in a magnetic field.
Exactly right. You put it in a magnetic field. So you have, by this time, instead of just the electroscope, they had a cloud chamber, which gives you a two-dimensional picture of these things going through the cloud in your big jar. And particles generally just go straight through. You get a straight line. But if you put a big magnet by it, then the particle will veer into a circle leftwards or veer into a circle rightwards, depending if it's charged positively or negatively. Also, the curvature of these loops will tell you the mass. Things of the big mass, they just keep on going straight and hardly bend at all. Little ones bend right away. So from watching these, you could see a whole bunch of protons or things like that. Then you found electrons, which bend more, and some were going leftwards and some were going rightwards. So that was what he finally decided by that. That was very, very clever to do. And then the muon was discovered by J.G. Street and E.C. Stevenson, again in a cloud chamber at the surface of the Earth. And so a muon, mu means medium. So it's medium in mass between an electron and a proton. Electrons are wee little tiny things. Protons are big heavy things. And so it's the electrons that go around the proton, right? And then the muons are of intermediate mass between the two. And they come plus and minus as well. And then some people did cosmic rays by looking at stacks of photographic emulsions. Something would come through and make a different size image on each of the emulsions. In 1938, Pierre Auger discovered with extensive air showers, he used detectors up in the Alps. So he had sensors and he took them up mountains, big mountains in the Alps. And then he'd find a little plateau and he'd separate these things by several meters and find how big an air shower there was. And the idea was if the incoming particle had a lot of energy, it would make a big fat air shower. If it had just a little bit, it'd make a little skinny air shower. And he got up to energies of 10 to the 15 electron volts, way above things that even now we could make in an accelerator. But I want you to remember 10 to the 15 because we're going to come to another number, even bigger, real soon. How can we explain this very high energy? I mean, this was enormous energy. Here are several ideas, and the answer at the bottom is we still do not know which one of these is most important. Could be protons accelerated by randomly moving magnetic mirrors in the interstellar medium. That's what Fermi thought, 1949. So there's
Well,
magnetic things, fields in space, and if some of them are moving this way and something comes this way, you could whap it and accelerate it. Supernova explosions, certainly. Shock waves come out from the death of a massive star, and that could certainly accelerate a whole bunch of stuff. That probably is one of them. Uh, or super bubbles, which are multiple supernova remnants going off pretty much at the same time in a star cluster. That would do it. Quasars or colliding black holes would certainly provide the energy necessary to do this. We do not know which of these it is. It's probably a combination of ingredients. There you go. In 1966, the GZK limit was proposed. So this is Greisen, Zetzepin, and Kuzmin, three different people, that there was an energy 5 times 10 to the 19th, or in fact 10 to the 20th, is the most energy that a proton could have coming from distant space. Okay. They had already measured 10 to the 15, but 10 to the 20 is quite a bit more, right? And the idea here, so this was just after the discovery of the cosmic microwave background, that the universe is filled in a very dilute sense with microwaves from the Big Bang explosion at the beginning of the universe. And if a proton just coming along hits one of these photons, so a light particle, it will lose energy. And if it hits another one, it'll lose even more energy. So if you have something from more than several galaxies away from you, it will drop down from 10 to the 20th to 10 to the 18th or so energy fairly quickly. So what this says is that there should be fairly few of the really high energy ones. And if you see one, it comes from nearby before it's had a chance to be slowed down. So that's a little scary, I think. But at any rate, very few particles above this cutoff have been found. There's one at 2 times 10 to the 20th, another one at 5 times 10 to the 20th. But it's really very few of them have been discovered. So this is quite a good result. And from something at ground level, you can learn something about the cosmos as a whole. I think that's really cool. Also want to tell you that I worked for Greisen as an undergraduate. I was part of his research team and helped build some apparatus that then had a awful failure. I'll tell you about that some other day. Because cosmic rays are charged particles, so they're always plus or minus, mostly plus, they're mostly protons or combinations of protons, they're plus, right? Their path is bent by magnetic fields, so that start going in these little circles. And magnetic fields are common in galaxies. They're weak, but they're all over the place, and they are of different orientations, so they're not uniform as one might hope. So the measured direction that you see a particle coming in on is not the original direction. So we could say, oh, I measured this one in my apparatus, my cloud chamber, and it came from constellation Hercules. Well, it probably didn't start in Hercules. It probably started over here somewhere and zigzagged around and finally came to us in that direction. So this is one of the big problems why you cannot tell where they came from. And nobody's found a way around this yet. So you say, well, oh, how about we use a neutral particle? Well, the main neutral particle is called a neutron, and a free neutron decays in 15 minutes. That doesn't get you much, does it? Oh, shucks. So I want to tell you about what cosmic rays we see at ground level are. They're the muons. Okay. everybody should hold out their hand. Your outstretched hand could be this way or you're up this way, I don't care, right? 2 particles per second are going to pass through your hand, and they are muons. And we've had now several seconds, and several 2 particles have gone through your hand. This is on average, right? But I don't think that's very frightening. It's interesting, but not frightening. But then I realized that the size of my hand is also the size of my brain. And so in the same time, 2 other particles have gone through my brain. And they're ionizing particles, and they could do some damage to DNA. This is something to think about. At the top of the Earth's atmosphere, the cosmic rays are mostly protons. 80% are protons, 15% are helium nuclei, and then the other 5% are other nuclei, nuclei of carbon or nitrogen or iron or anything else. There are small bits of those things, and some people are very keen to measure those. They're moving very fast, 99.99999% the speed of light. So they're really zinging along. Why do the muons particularly survive to reach sea level? They have what we call a longish lifetime before they decay. All the others decay really quickly, and they decay in microseconds, which is considered long. It's long microsecond, right? And they do not interact with the electric fields of atoms as much as electrons do because they are heavier than atoms. The heavier they are, the more you can keep on going. The lighter you are, you get all bound up in something you pass by too closely. So they come pretty much straight down and they last microseconds. But that should be not quite enough to get them from 100 kilometers down to sea level. They should decay at the tops of mountains, but they don't. Because we have Einstein. So I thought I'd show you here a measured spectrum of cosmic rays. These are inferred. So from the size of the air shower, you infer the energy of the primary cosmic ray. Energy is across the bottom here in powers of 10. And you see it goes up to 10 to the 20th and at the corner 10 to the 21st, but there's nothing there. The flux is on the vertical scale, how many of them you get. And if you look at the first blue thing up there, it's 1 particle per square meter per second, is at the 10 to the minus 1 flux level. Then you get down to where it's marked Ni, 1 particle per square meter per year. You have to wait around for that one. And then down to the bottom where it says Ni, 1 particle per square kilometer per year. That's a big thing. So these are hardly here at all. But look at the very bottom there, and you can see the drop off right above 10 to the 20th. There are very few particles there. That's the ZK limit. Okay. Well, to find and measure rare events, we need a really giant detector. So they've built one in South America. Cool. It's the Pierre Auger Observatory in Western Argentina, where there are lots of big fields with nothing on them except these detectors. They even put it on a stamp. See on the right there, a stamp, the Republic of Argentina. And this is what it looks like. So here's one of the physicists changing one of the batteries in this thing. And there's a wild goat sort of looking at what he's doing. So these are they have 2 types of detectors down there, Cherenkov and air showers. So the Cherenkov detectors are looking at particles that are going faster than the speed of light in water. So this whole thing is filled with water, and it has photomultiplier tubes around the outside to look at the water. And if a particle is going faster than the water light speed, which is only 75% of the speed of light in vacuum, then it makes a little flash of light. So they record the flashes of light. Just to give you an idea of the size of these things, there's 1,600 of them spread across the pampas there, 1.5 kilometers apart, 3 photomultiplier tubes each. They measure the time very accurately, and they can figure stuff there. The other type of apparatus they have is fluorescence of nitrogen in the atmosphere. They have these detectors that look upwards into the air. Charged particles, very high energy, cause nitrogen to emit ultraviolet light. So looking at ultraviolet light from the sky, flashes of it. And they can measure stuff up to 15 kilometers away from the detectors. They have a bunch of these around there too. Their data is public. You can go look at it. We'll do that slide later. If you have a series of them, this upper graph here shows you the distribution of energy from the center of the shower outwards. And you can see it does have a nice logarithmic decay. So it is an organized thing. And so the bottom picture on the left is an all-sky picture of the universe. The bright line across the middle is the Milky Way as we see it. And then in the upper middle, there's a little blue circle, and that's where they think one primary cosmic ray came in. And it's from Virgo, and that's interesting because the Virgo cluster of galaxies is the largest interesting source of mass in our neighborhood. Not sure that's meaningful, but it was sort of cute. Now we want to talk about things that are more local to us, the solar system and the Earth. So the Earth's got a good magnetic field. It's sort of, the traditional apple-shaped lines of force. But the solar wind is pretty fierce. And here we have a picture, a diagram, not a picture, a diagram, which is not to scale, of the sun putting out the solar wind, which then comes and impinges on the Earth's magnetic field. What this does is it pushes in the Earth's magnetic field on the sunward side and draws it out into a long, long tail on the midnight side. This protects us from most low energy particles, only 10 to the 8th electron volts, not 10 to the 20th. But then there are ones that are slightly above that can get through. So one of my favorite pieces of craft apparatus is made of pipe cleaners. So this is my pipe cleaner view of the Earth's magnetic field. Here's the Earth. Here's the sunward side. Here's the side that goes out toward midnight. And these magnetic field lines are in all sorts of movement at different time scales. So one of the interesting things, of course, is that the sun has gusts in the solar wind, and that pushes this in on this side, which of course then wiggles the tail something awful too. And so we have all sorts of interesting radio consequences of that. And all sorts of particles get stuck in here too. Okay. Here's a version then of the next scale up, and that is that the sun has a heliosphere. So in the middle there, that little white dot is supposed to be the sun. We have the whole solar system of planets near the center of that going outwards. And then on the left side of this one is a big band of turbulence, which is to represent the solar winds coming from other stars. And if everything were static, this would be around and it would be a circle, a sphere, but it's not. The solar system is moving through our region of the interstellar medium, and in this picture, we're moving leftwards. And so we are running into the influence of other stars, and so that pushes in the sun's influence on that side, draws it out on the other side on a much, much larger scale. And what I want to point out here also is that there's a bluish thing, which is the termination shock, where it begins to be that the Earth's, rather the sun's magnetic field is being nullified by the ones from other stars. But then beyond that is the heliopause, the ends of the heliosphere, and that's where truly you go from the sun's influence, the outflowing of the solar wind to a sort of a bubble-like structure, and then finally you get out to interstellar space where other stars rule. And there's little indication there of Voyager 1 going up, Voyager 1 going 2 downwards. These spacecraft have now passed the termination shock and passed the heliopause and are now in interstellar space. They're outside the sun's influence altogether. So that's how you calculate that. Forget that. So one of the interesting things, I think, is that if you measure cosmic rays on the ground here, and you measure them for more than 11 years, then you could find that the number of cosmic rays is anti-correlated with the number of sunspots on the sun. Isn't that the coolest thing? I love this picture. So the blue line there is cosmic ray intensity. And so it goes up and then it goes down, and then it goes up and then it goes down, and it goes up and it goes down. But the green one, the green line is the number of sunspots on the sun, and that goes down, and then it goes up, and then it goes down, and then it goes up, and they're opposite to each other. So the interpretation of this is that when there are more sunspots, there's a more energetic solar wind. It blows more and it blows faster. And the solar wind then extends further into space and pushes off the interstellar boundary somewhat a bit, and it blows some of the cosmic rays out, which are coming to us from all different directions, but it blows some of them away, makes them lesser. I think this is wonderful. Don't you like this one?
That's nice. I like
It's
that.
it's
Uh,
just nice, isn't it? It's nice when something is easy to understand. I think so too, Glenn.
It's very counterintuitive. It doesn't make sense,
And then you go, oh, but it does make
but it
sense.
does. Yep.
It does. Now I understand it. Let's go back and look at that again. Isn't that beautiful? And if the solar cycle is long, the cosmic ray cycle is long. And if it's short, the cosmic ray one is short as well. So if you look toward the middle, the 1975 one was fat, and the 1985 one is skinny. So 11 years is only an average. So that the solar cycle goes from I don't know, 10 to 14 years. It's not as clean as one would hope. But it is repeatable. So in some sense, I think this is lovely. All right. So next I want to tell you about what we did at Montclair State. So in 2011 and 2012, I managed to borrow some material from Rutgers University here in New Jersey, but they got it from Argonne National Laboratories in a project called Fermi Lab QuarkNet, in which they had sensors of cosmic rays, and they would give you the pieces, and then you had to assemble them, and you could have them for 2 years, and then you give them back. So we had them for 2 years, and we gave them back. But first thing was to assemble them. That was not as easy as we thought it would be. Okay, so you got a slab of clear scintillator plastic. So it's pale blue, if you could just see the edge of it there. And it goes back, it looks like a small window frame. It's an inch thick. Clear plastic, but if you look at it, oh, it's a little bit of blue on the edge. And it's doped with some chemical such that when a charged particle comes through it, it flashes and gives you a flash of light. And then you got one photomultiplier tube to glom onto the edge of this and wrap the whole thing till it was light tight. Okay. So here's the photomultiplier tube. That's what it looks like if you look right down it. And here's the team we started with. Jessica McMasters is in the black on the left, then me, then Steve Schnetzer from Rutgers, and then Elaine McCarthy is in the blue shirt on the right. Those two are middle school science teachers. And then I had my college students, but they were not in this picture. So this is the box. We opened a box, and in the white package in front of Steve, there's the scintillator plastic sheet. Jessica's holding some PVC tubing, And there's other pieces lying on the table that have to all be assembled together, including the electronics. So that's where you get. So each paddle had to be wrapped in aluminum foil, then black paper, and lots of black duct tape. There could be no light from the room getting into this thing. So it's a black thing, and it comes out only through this photomultiplier tube, goes to the electronics box, and then to your computer. So here's the first wrapping. And there was lots and lots of electrical tape as well as duct tape being used. And here's my undergraduate Tim Reese wrapping. And you can see on his lap is the already wrapped plastic bit, and now he's wrapping the tube to the side of it that has the photomultiplier in it. So once you get it all wrapped and everything is perfectly light tight, and you have to do that several times, then you have to calibrate each of the paddles. And so this was our first one, and measured various voltages to the equipment. So you keep turning up the voltage and measured the counts. And you get a sort of a mildly S-shaped thing. What you want to do is to find where the linear part is in the middle here. And you pick your voltage off of that. And for this one, we picked 714 millivolts. So that's sort of in the middle of the thing. And you see that was where the curve was pretty much flat. That's where we set it for, so we would get a linear response. Now the muon's lifetime is elongated by its very fast velocity. All right, it's coming in at 99.9, a little less, the speed of light. And Einstein had said that fast-moving particles have a slow clock. So it's called the time dilation effect. It was predicted in 1905, which, by the way, is over 100 years ago, right? And we could measure the lifetime of the muons, which stop in we chose the second paddle to have them stop in, and see what it came out to be. So here's the curve. So this is what Tim measured. The decay time in microseconds is across the bottom, 0 to 4 microseconds. We have a confidence that we're getting a tenth of a microsecond accuracy. He counted 2,500 individual particles. And you can see that that's a really nice curve. The R-squared value is 0.996. Pretty good, right? And from that, you can then back out the lifetime, because the lifetime is 1 divided by the exponent of the logarithm there. It's 1 over 0.489, which you can see is up there. And that came out to be 2.04 microseconds. The accepted value is 2.20 microseconds. So we're within 10%, not bad at all. So he was pleased as punch that we had measured this. So here we are at the science fair. Tim is the one on the left in the beige shirt, and that's his poster, cosmic rays behind him. And then on the right is, because he happened to be in the same thing, Matt Rossi, who did a project for me that year also in quasars from data from other places. So they were both very pleased to have measured something really cool. Then we had another whole set of projects where you use the cosmic ray not as just itself, but as a probe of ceilings, or what is between you and the sky. People had used it for the Egyptian pyramids, which they didn't see very much. They didn't see anything that was unexpected. So although all solid materials are mostly empty space, there's a small chance that a cosmic ray will actually hit the nucleus or hit one of the electrons and be stopped. Okay. And so the more material it is, the more there's a chance of it getting absorbed. So the question is the absorption proportional to the amount of material above the detector? And can we use this to judge the thickness of a ceiling, which is usually multiple types of stuff all together? So we thought we would do that. That sounded like fun. So here's the way you set up the experiment. You wanted to have something, a particle that went through so we had 4 of these scintillator plates, went through the first one, did not go through the second one, got stuck somewhere between them. And so you could do all sorts of experiments with putting stuff in there, the absorbers between them, or having a ceiling between them, okay? I want to point out the third line down, coincidence window is 0.1 of a microsecond, and the gate width was 0.2 of a microsecond. So that's what determined our accuracy in time. Here's the results. This is what Will got. These are just arranged in rank order. The strength of the ceiling, how thick is the ceiling above you? So the first 2 things are Schuyler School and Richardson Hall, and then Science Hall, and then Franklin School and Lincoln School. These are all school buildings which were sturdy, made of concrete and iron and stuff like that. So those are good. Then we get to the parking decks. Parking decks are not so strong. And finally, we got to wooden houses. Went around and we measured everybody's house in the group, and they have sort of flimsy stuff between you and this guy. So here's Will with his poster, muon absorption of structures varying in age and material. It did come out slightly that the older structures built around 1900 were thicker than structures built in 1980, and wooden houses were thinnest of everything. So that was fun for him. Then here was one that I thought was really great fun. So Schuyler Middle School in Kearney, which is over that way about 10 miles, we measured. So the 2 middle school teachers took the paddles on a cart and took them to various levels within their schools. And so on the left-hand side, we have the original data from Schuyler School and the number of ceilings. So 0 is you're on the roof, 1 is in the top floor, 2 ceilings is down the next level, right? And here's what the data looked like. And it didn't make a nice curve. There's one peculiar piece above the number 1, which is not fitting there. But we did find if we made 1 into 2 and moved it over, then we get the second graph over here, and now they fit. Look at that, nice curve there. So that meant that wherever number 1 was, didn't have just 1 ceiling above it, it had 2 ceilings above it. So that was the art room in the school. So Elaine went to the principal and said, we seem to have found that there's a double ceiling in the art room. Why would the art room have a double ceiling? And he goes, oh my God, you're not supposed to know that. What? Well, there's a storage room, a little thin storage room above the art room. So it's got a lowered ceiling, but it's a real ceiling, not just these little tile things, a real ceiling. And it's got paint cans up there. You're not supposed to know we've been keeping those up there. Don't tell anybody. Next. So we had to thank Steve Schnetzer from Rutgers, who arranged for us to get these for 2 years. The Fermi Lab people, the Argonne Labs near Chicago. We also cooperated with Joe Spacavento at North Arlington High School. And then, of course, Elaine and Jessica at the Kearney Middle Schools. It was quite a wonderful project. So here's the summary of what I wanted to tell you today about cosmic rays, and then you can ask questions. They're energetic protons. We don't know their source yet. They do have a high energy cutoff, so the number goes down, and then there's a cliff at a little over 10 to the 20th electron volts. They are repelled somewhat by the solar wind, and that is sometimes said that the whole heliosphere breathes on an 11-year cycle. I don't know about that. They do break up in our atmosphere, and some muons can reach ground level, and they can be measured by students if they have fancy equipment. Thank you very much.
Wow, that was
That
fantastic.
was cool.
What do we have for questions?
Hey, Mary Lou.
Yes. Hi,
So,
Ron.
so, so something I'm curious about, since I've never taken a physics class,
Oh, you ought to
is
sometime. It's great fun.
the these these cosmic rays that are traveling such great distances at such high speed. Where does the energy come from that over a period of time they can keep moving that fast? Is there no law of friction to slow them down, no law of anything to slow them down, that they can keep that speed up going that distance? Or is it they have such high energy that that keeps propelling them? I think I'm missing something as to how they can go that far and not just eventually peter out and quit moving.
Right. Okay. So what you're missing is space is empty. So you have friction. Friction would slow them down, sure. Friction, you have to rub on something. You have to hit something. You rub on it. There's nothing to rub on except the cosmic microwave background. So that there's very few things in space. So there's a couple of stars, there's a couple of planets. That would stop them for sure, right? There's a couple of protons in the solar wind. There's the solar wind of other stars. But that's really, really minuscule stuff. There's just nothing there. So they don't slow down. Most of them, well, many, we don't know most, many of them don't slow down at all. They're ejected from something like a supernova, who knows, whatever, ejected. They sort of meander a little bit, magnetic fields, and they hit the Earth. And they're still going at 99.9% the speed of light. Space is empty. That's why we
Okay,
call it
thanks.
space. But it truly is amazingly empty.
Just question, for these like ceiling measurements or whatever, how long did it take to make the measurement? Number of minutes or hours or whatever.
Yeah, each of the measurements was 1 minute of time, and it was repeated. So they had another, say, 2 minutes. Um, so they would do um, 2 minutes on the first floor. Then they'd take the elevator down to the next floor and do again 2 minutes, right? And then they'd take it on the elevator down to the next one, 2 minutes. So in an hour, you could certainly have a cup of coffee and do a whole school, you know, and then you had to go home and figure out what the numbers meant. You'd um, read them off the machine and that sort of thing. But it was not a long experiment um, to do. Oh, so one of the ones that really confused Will and me is that one of the objects we did was the new parking garage at Montclair State. So we put these paddles in my car. We drove up to the top level, did our 2 minutes, closed it up, came down to the next level, parked directly under the last spot. Again, 2 minutes. Did the whole thing. And we got back um, to make the curve. The curve was really nice curve, except 1 point. 1 point was off. What was wrong with that point? Went and remeasured it. Same thing. What we finally discovered, took us a week to think about this, is what did it mean to be right under the same place? And what had happened is on that floor, whoever had drawn the lines on the ground that said park here, park here, park here, park here, had moved them over a foot. And that meant where I put the car, it was under a beam. We discovered a beam, a concrete beam. You could look up and see the concrete beams, but we didn't look up until a week later. And we
Man.
found the beam.
How big was the instrument when it was assembled? that you had to take from one floor to the other?
So the stack of paddles fit in a cardboard box. Um, 2 feet by 15 inches, that sort of size. So we had a cardboard box with these things stacked up in them, and the wires coming out and going to the electronics. So you had a little electronics package. Um, and we found that the easiest way to move it around was to get one of those little moving carts like a T cart and put it on that, and the electronics were underneath. And that, because that could go into elevators and up around rather than carrying the box.
Hey, Mary Lou, that cutoff at 10 to the 20th EV, I'm really puzzling over that. I hadn't heard of that, and I don't quite understand that mechanism there. That interaction. So that's a photon interacting, cosmic microwave background photon interacting with a particle of that energy. What's going on when you exceed that energy? I guess I don't understand that
Okay,
process.
so it is a longer calculation. But the idea is if so for all the cosmic rays that come out of whatever the source is, um, space is pretty empty, except there are a fair number of these microwave photons. So that's the only thing you could rub on is the microwaves.
Mhm.
And so all of them would rub on the microwaves, and so the energy would come down. But particularly if you're above a certain energy, it really rubs a lot. And that cuts those off most particularly.
So it's affecting all of them, but just when you get to that energy, it's a
It
more
really whumps them
dramatic.
down
Yeah.
right away.
Hmm.
Yeah. They hit
Okay.
one and they're down.
Yeah.
Yeah.
Gotcha. Thanks.
So the one American, Greisen was the American who thought about it and wrote a paper, and then the two Russians thought about it and they wrote a paper, and then somebody said, "Aren't these the same?"
Hmm.
Yeah, they are. They are.
Cool.
Mary Lou,
Yeah.
how does the OMG particle fit in that? Would that be an outlier case, or is that the oh my
Uh,
God particles?
yes. I'm not sure exactly what you're thinking of, but one of them that's higher energy. Is that what you're thinking of?
Well, they're a lot higher energy, is my understanding. It's like 99.99999 to the 28 places of light.
Don't know. Have to look that up.
Mary Lou, I have a two-part question.
Yes, Glenn.
Okay. First one is when that, don't call it a cosmic ray, when that cosmic bullet hits something, it deposits its energy in some way.
Yes.
So if it's, we've heard about hitting a memory chip and knocking out a bit, all right. What if it hit you in the brain for the neural pathway that says, "How do I hold a pencil?" So it could literally hit anything
That's
and
true.
cause
Yeah.
damage.
Right.
So the damage, what happens at that point? I guess it's whatever target we're hitting. Are we hitting organic matter or are we hitting a piece of lead? Right. So it depends upon that. But it does impart energy into it. Now, once it does that, is it dissipated like at that point, or is it decaying again into other particles?
There, there's a whole series of things that can happen, but um, basically the particle comes, hits something, deposits its energy. This thing breaks into little pieces, and then there's a proton just sitting there by its side. Or the proton itself breaks into little particles as well. Um, so if it hits your brain, then some little memory thing is whacked up, but the neurons are fairly fat. They got a whole bunch of atoms in them, and if only one of the atoms is whacked up, maybe it's not too bad. And then they have, lots of little neurons in there too. So people are not worried about your brain so much. It's pretty redundant, but they're more worried about DNA in um, your cells that are going to make babies, right? Because that could really mess it up. And so maybe some of the, things that people are born with that are some peculiar enzyme thing might have been caused by a cosmic ray in one of their parents. We don't know. We don't know what caused this. So, well, it just happens,
Okay.
That could be. Um, and certainly, uh, if you have memory chips and th electronic things that are sensitive, you should harden them to go in space, and they are generally hardened or almost all cases duplicated. Usually three of them. So if something happens, then they all three vote. So two
They
of them
vote,
say
right.
this, you go with the tour and say
Yep.
that's what's going to happen.
Yeah. Although
Yep.
a lot of hardening
And
has really gotten rid of a lot of the triple mode redundancy. So there's been a lot of work in radiation hardening of the actual chips themselves because they were chewing up so many resources doing triple mode redundancy in stuff or whatever. And they're like, why are we doing this? Let's just design better chips.
So how do they design the chips? Do you understand what they do to make
Uh,
that unnecessary?
um, a lot of it is materials. Like before I left work, there was a group down at Georgia Tech, I think it was. They were involved in doing a lot of studies of things like silicon germanium and the radiation tolerance of that. Um,
So
so
you,
there,
so you get big, heavy atoms to
yeah,
work for you. Okay.
yeah, and also like the single event upsets that happen like in space or whatever. There's a lot of things too where the um, oh shoot, there are certain band gaps or whatever that are more resilient apparently to some of the energy. So there's less of an effect than they used to have, I guess, with some of the other older materials, um, to prevent latch up and things like that. But yeah, actually, there's been a lot of work in there. Apparently, there's also been a lot of interest too in trying to leverage parts that are rated for the automotive industry. Because uh, I guess because they've seen that their ability to operate at higher temperatures or whatever was actually causing them to actually have some better properties or whatever that were slightly more favorable in a radiation environment. Um, so yeah, there was a lot of work going on, and that's where a lot of the chip manufacturers were really starting to look into that because they were catering to the space market for all the low Earth orbit satellites that were going to be produced. So that's where, like I said, they were looking at that. There were other rad-hard plastic enclosures that were being fabricated also that the plastics were a certain material or whatever. They minimized the amount of um, stray particles or radiation or whatever that were actually affecting things at the dye level. So yeah,
Thinking
there's a lot of like that.
thinking about enclosures, so one of the things the manned space program thinks about is how to protect astronauts from low-level cosmic rays
Mm.
when they're going toward Mars, because the sun's spitting stuff out all the time, and if it spits out a big bunch, then the people are more likely to get cancer or something. So the idea was that you would build a closet inside the spacecraft, whatever it is, and have the walls lined with the water supply is pretty good or something that's just and everybody, if so if solar storm comes, everybody gets in the closet and stays there for 4 hours or whatever. Um,
I think
but
they call
yeah,
it the pillow fort.
the pillow
There's a
fort.
video
That's
when
it.
they
Yes,
testing it. Yeah,
that's
water
great.
is really good for dealing with that.
That would be good to see. Yes, yes. And so an enclosure for the electronics would be a good thing in
and
spacecraft too.
my second part.
Yes,
Will you be releasing the pipe cleaners as a kit?
no, but I got this from a NASA site for children. And I thought this is really cool because it's really dynamic,
That is cool.
you
Yeah.
know, and also, so one of the interesting things, of course, about the Earth. So this is the Earth here, but it's rotating within this. So if you're on a piece of the Earth, your magnetic field is like this for a couple hours, and then it goes in, and then it's suddenly like this. So you have a diurnal thing in your magnetometer, which just explains how you're rotating within this sort of cage-like affair. But then, of course, it's dynamic on time scales of seconds and minutes and hours and 11 years and stuff like that. So that's what we're going to learn from our little magnetometer things.
So Mary Lou, I think
I had,
reminding us that space is very empty is a valuable lesson because as I sit here and we think about coronal mass ejections and solar flux and all that sort of stuff, and we realize that we're just a really pretty tiny speck in the whole big picture. But how about these cosmic rays and the effects of black holes? Because we seem to be finding more and more of them with our new telescopes and whatnot.
Right. Well, so my take on black holes is that yes, they're very dangerous, but they're very tiny and they're very far apart. They're like ticks. So you don't want to mess with them. But they're little tiny things, and and we now have ways of figuring out where they are. If you're close to one, you go, oh my God, there's something over there. Well, then go away from it. Don't go by it. It's like you're going down a highway and there's suddenly all sorts of flashing lights and things off to the side. Well, don't go over there. Go in the left lane and go past it, you know. Um, so yes, they're very dangerous and they're scary and everything, but you can avoid them pretty easily if you pay attention. You know, even if you can't see them, you can detect them. So I don't think they're as scary as people make out.
I just had a comment. So I attended a talk at the Eastern Great Lakes section meeting of the American Physical Society over the weekend, and it's sort of a compliment to your talk in some ways. So the professor, her name is Mayor Nisa, she's at Michigan State University, and her talk was about neutrino observatories, and the idea of because cosmic rays are charged, they're not great for doing astronomy of some sort. But the neutrinos are very weakly interacting because they're not charged. And so they're now building these observatories down, as you probably know, in Antarctica and other places to try to measure where they're coming from. And the challenge there is that they're so weakly interacting that you have to wait a long time
They go right
to
through
find
you.
them. Yeah, they go right through you. Trillions, trillions, trillions are going through you at any moment. Anyway, I thought it was a nice kind of an interesting postscript to this talk.
Thank you. I should have mentioned neutrinos, but I think they don't care and they go right through your apparatus and they don't register. So it's really tough. But Ice Cube is a good way I mean, they have partial handle on that. So
And they use a similar approach, right? They use the Cherenkov radiation detectors to find the neutrinos the same way.
yeah. Yeah. Thank you. That was cool.
Okay.
So
Yeah,
Mary
put some
Lou,
links in on the rad hard by design stuff that's going on now.
the ceiling detector you talked about, you said it was roughly 2 feet by 15 inches. Did a
Yes,
lot of good science with that. And, and
I will find a picture of it and put it into this before I send it to you and you could then post it. But
okay,
get a
but
picture.
the folks in Argentina were doing the same thing, but just on a much larger scale, right? 3,000 kilometers, 1,600 tubs of water. That's just amazing that somebody has the chutzpah to say, okay, we can do this in 2 feet by 15 inches, but I want to expand it over 3,000 kilometers. So good for them, I guess is what I'm thinking.
Yes, I thought that was an amazing, amazing thing. Um, but evidently there's only a few goats there and that's all. So I don't know. I've never seen it.
Wow. And nobody asked the goats, but that's okay. So great. That's a heck of a lot to think about. Any other comments or questions for this evening for Mary Lou?
If you
That's
think of
pretty
questions
cool.
later, we'll do another thing. But this is the last one till what, September?
Yeah, probably. Yes, probably till school starts again. So we've got the 3 or 4 months to think of questions. Once the video's up, run it by yourself again and write down more questions. This is great.
Yeah.
All right, everyone. Well, thank you very much, Mary Lou. That was just fantastic. That was a heck of a way to end our year. We had a lot of good talks this year, and this one's certainly up there with the best of them. So thank you very much.
Oh, thank you very much. So if you were in my class, so I'm a teacher. If you were in my class, I would make you all say together before you left the room, space is very empty. Okay. Bye.
All right, everyone. Have a great summer. Hope to see many of you at the Dayton Hamvention next weekend, or otherwise cross paths at a Ham Fest or at K3LRs or doing some field work with HamSCI. So take care, everyone. Enjoy your time on the radio and keep doing good science.
Thank you very much,
73 all.
Gary and Mary Lou.
Bye.
Goodbye.
Bye. Bye.
730.